The oceans cover most of our planet, yet much of how they work remains unseen. They move heat across the Earth, shape climates, and quietly support life everywhere, from the air we breathe to the food we eat. How can one continuous body of water behave so differently across the world? What connects warm tropical seas to cold polar waters? And how do slow ocean currents influence the planet without ever drawing attention to themselves? Tonight, we'll explore the oceans as living systems, their regions, their movements, their layered depths, and the steady rhythms that keep the Earth in balance. Hello, and welcome to the Sleep and Wonder channel. As you settle in, allow your breathing to slow. There's nothing you need to follow closely. Just listen and let your thoughts drift. If these quiet journeys resonate with you, you're gently invited to like or subscribe. But for now, simply rest as we begin our calm exploration of the oceans. Imagine yourself floating gently above the surface of the ocean, watching the water move below you. Slow, vast, and continuous. Let's begin. The ocean is the largest continuous system on Earth. It covers more than 70% of the planet's surface, connects all continents, and holds almost all of the water that exists at the surface of the world. From space, it is the first feature that defines Earth as a living planet, an immense blue presence that surrounds land, shapes climate, and sustains life. To enter the ocean as a subject of understanding is not to rush into its depths, but to begin with its scale. The average depth of the ocean is close to 4 kilometers. In some regions it descends far beyond that, forming trenches deeper than the highest mountains are tall. Yet most of the ocean remains unseen, not because it is distant, but because it exists beneath a surface that appears calm, reflective, and deceptively uniform. Despite its vastness, the ocean is not a collection of separate bodies. It is a single, interconnected system. Water circulates continuously, moving heat, nutrients, gases, and energy across the planet. A current that begins in one region may influence temperatures, weather patterns, and ecosystems thousands of kilometers away. In this sense, the ocean behaves less like a background feature of Earth and more like an active organ, constantly adjusting, regulating, and responding. What we often call the sea or the ocean is, in reality, a layered environment. The surface interacts directly with the atmosphere, exchanging heat and gases. Below that, layers of water move at different speeds and directions, shaped by temperature, salinity, and Earth's rotation. Deeper still, slow currents travel along the ocean floor, completing cycles that take centuries to finish. These movements are not chaotic. They follow physical laws that are remarkably stable over time. Gravity, density, planetary rotation, and solar energy work together to maintain patterns that have existed for millions of years. Even as continents shift and climates change, the ocean continues its circulation with quiet persistence. The surface of the ocean is where most human attention rests. Waves rise and fall, driven by wind and distant storms. Tides move shorelines rhythmically, guided by the gravitational pull of the moon and the sun. These visible motions give the impression of constant activity. yet they represent only a small fraction of what is happening beneath. Below the surface, light gradually fades. Temperature changes become more pronounced. Pressure increases steadily. Life adapts to these gradients in ways that are precise and efficient. Each depth supports organisms suited to that specific combination of light, pressure, and available energy. Still, the ocean is not divided by strict boundaries. Water masses mix slowly, nutrients travel upward, organic matter sinks downward. Sound moves farther here than in air, carrying information across vast distances. In this way, the ocean remains unified even as its conditions vary dramatically from surface to depth. From a planetary perspective, the ocean plays a stabilizing role. It absorbs and redistributes heat, preventing extreme temperature swings. It stores carbon and releases oxygen through microscopic life. It buffers the atmosphere, moderating changes that would otherwise be abrupt and disruptive. Without the ocean, Earth would not function as it does today. Its presence allows climates to remain habitable, seasons to follow predictable patterns, and ecosystems to establish long-term balance. The land, the air, and the ice all respond to the ocean's movements, often in subtle but essential ways. To enter the ocean as a subject, then, is to recognize it not as a distant or separate realm, but as a system that quietly supports everything familiar. Its influence extends into the air we breathe, the weather we experience, and the rhythms of life on land. As we begin this journey, there is no need to imagine descent yet. For now, it is enough to remain at the threshold, observing the ocean as a whole, understanding its scale and acknowledging its role as a continuous presence on Earth. From this broad view, we can begin to notice how this single body of water expresses itself differently across the globe, forming distinct regions, each with its own characteristics, temperatures, and histories, yet all connected beneath the surface. That is where we gently move next. Although the ocean is a single, continuous body of water, it is traditionally divided into distinct regions. These regions, known as the world's oceans, are not separated by physical barriers, but by geography, circulation patterns, temperature, and historical convention. Each ocean has its own characteristics, yet all remain deeply connected beneath the surface. Today we recognize 5 main oceans: the Pacific, Atlantic, Indian, Southern, and Arctic oceans. Together they form one global system, but each expresses that system in a slightly different way. The Pacific Ocean is the largest and deepest of them all. It covers more surface area than all land combined and holds the deepest known point on Earth, the Mariana Trench. The Pacific is shaped by vast tectonic activity, with long chains of volcanic islands and deep trenches marking the boundaries of tectonic plates. Its scale allows for immense circulation patterns, including some of the strongest and most influential ocean currents on the planet. These currents help regulate temperatures across entire continents, influencing weather from Asia to the Americas. The Atlantic Ocean, though smaller than the Pacific, plays a central role in global climate. It is narrower, which allows water to circulate more efficiently from north to south. One of its most important features is the Atlantic meridional overturning circulation, a system of currents that transports warm surface water northward and cold, deep water southward. This movement helps moderate temperatures in Europe and supports stable climate patterns that have existed for thousands of years. The Indian Ocean is unique in its interaction with seasonal wind systems. Monsoon cycles strongly influence its surface currents, causing them to reverse direction throughout the year. This makes the Indian Ocean highly responsive to atmospheric changes. It is also one of the warmest oceans, with large regions of consistently high surface temperatures. These conditions support rich marine ecosystems, coral reefs, and complex interactions between ocean and atmosphere. The Southern Ocean encircles Antarctica and is defined more by movement than by land boundaries. Here, the Antarctic circumpolar current flows uninterrupted around the globe, linking the Atlantic, Pacific, and Indian Oceans. This current is the strongest on Earth and plays a critical role in global circulation. The Southern Ocean helps isolate Antarctica thermally, maintaining its ice sheets and influencing sea levels worldwide. The Arctic Ocean is the smallest and shallowest of the five. Much of its surface is covered by sea ice for large parts of the year. Despite its size, it plays a disproportionate role in regulating Earth's climate. The Arctic reflects solar radiation back into space and influences atmospheric circulation patterns across the Northern Hemisphere. Changes in Arctic conditions can have wide-reaching effects far beyond the polar regions. Although these oceans differ in size, temperature, depth, and circulation, they are not independent systems. Water moves continuously between them through currents that span the globe. Heat absorbed in one region may be released in another. Nutrients transported across thousands of kilometers support ecosystems far from their source. From a physical perspective, the differences between oceans arise largely from three factors: latitude, basin shape, and connection to other water masses. Latitude determines how much solar energy reaches the surface. Basin shape affects how currents move and interact. Connections to other oceans allow for the exchange of water and energy. Biologically, each ocean supports distinct ecosystems shaped by these physical conditions. Cold, nutrient-rich waters often support high productivity, while warm, clear waters tend to support coral-based systems. Depth also plays a role, as pressure and light availability change with distance from the surface. Human history has been closely tied to these oceans. Trade routes, exploration, climate patterns, and food systems have all been shaped by their presence. Coastal civilizations developed in response to the rhythms of nearby seas, learning to navigate currents, winds, and seasonal changes long before modern science could explain them. Despite centuries of study, much of each ocean remains unexplored. Large areas of the seafloor have never been mapped in detail. Deep currents are still being studied, and new species continue to be discovered. The oceans we name and categorize remain, in many ways, only partially known. Understanding the oceans of the world is not about dividing the sea into separate parts, but about recognizing how a single system adapts to different conditions. The ocean changes character as it moves across latitudes, encounters land, and responds to planetary forces, yet it never stops being one connected body of water. As we move forward, this idea of connection becomes even more important. Beneath the surface divisions of maps and names lies a shared structure, layers of water shaped by light, pressure, and motion. To understand the oceans more deeply, we now turn our attention downward, toward the vertical dimension of the sea, where depth begins to transform everything it touches. When we think about the ocean, it is common to imagine its surface, waves, reflections of light, and the movement of water under the sky. Yet the ocean is not defined only by its horizontal extent. Its most striking dimension lies downward, in depth. The ocean is a vertical world, structured in layers that differ dramatically in light, temperature, pressure, and life. Scientists divide the ocean vertically into zones based primarily on how sunlight penetrates the water. These zones help us understand how physical conditions shape biological activity and how life adapts to depth. The uppermost layer is known as the epipelagic zone, often called the sunlight zone. This layer extends from the surface down to approximately 200 meters. Here, sunlight is strong enough to support photosynthesis. This single factor makes the epipelagic zone the foundation of nearly all ocean life. Phytoplankton, microscopic organisms that use sunlight to produce energy, thrive in this zone. They form the base of the marine food web, supporting everything from small zooplankton to large predators like fish, seabirds, and whales. Although phytoplankton are tiny, collectively they play a major role in regulating Earth's atmosphere by absorbing carbon dioxide and producing oxygen. Water temperature in the epipelagic zone is relatively warm compared to deeper layers, though it varies with latitude and season. Surface currents driven by wind and Earth's rotation are most active here. These currents distribute heat and nutrients across vast distances, shaping climate patterns and marine ecosystems. Below the epipelagic zone lies the mesopelagic zone, sometimes called the twilight zone. This region extends from about 200 to 1,000 meters below the surface. Sunlight still penetrates here, but it is faint and insufficient for photosynthesis. In the mesopelagic zone, light fades rapidly. Colors begin to disappear, with red wavelengths absorbed first, leaving the environment dominated by blues and grays. Temperature decreases sharply across this layer, creating a region known as the thermocline, where warm surface waters give way to colder, deep waters. Despite the low light, the mesopelagic zone supports a surprising amount of life. Many organisms here rely on organic matter sinking from above rather than local food production. This includes small fish, squid, and gelatinous animals that feed on drifting particles or migrating prey. One of the most remarkable phenomena associated with this zone is diel vertical migration. Every night, billions of organisms rise toward the surface to feed, then descend back into deeper waters before daylight. This daily movement is the largest migration on Earth in terms of biomass. It plays a crucial role in transporting carbon from the surface to the deep ocean, helping regulate global climate. Below the twilight zone lies the bathypelagic zone, often called the midnight zone. This region extends from about 1,000 to 4,000 meters deep. No sunlight reaches this depth. The environment is completely dark, cold, and under immense pressure. Temperatures in the bathypelagic zone remain near freezing year-round. Pressure increases dramatically with depth, reaching levels that would crush unprotected human structures. Despite these extreme conditions, life persists. Organisms in this zone have evolved specialized adaptations. Many produce their own light through bioluminescence, using chemical reactions to emit flashes, glows, or steady illumination. This light may be used to attract prey, communicate, or avoid predators. Eyes, when present, are often large and sensitive, adapted to detect even the faintest light. Food is scarce in the midnight zone. Most organisms rely on organic material falling from above, sometimes referred to as marine snow. This slow rain of particles, dead plankton, fecal matter, and debris, provides the primary source of energy for deep-sea communities. Beyond the bathypelagic zone lies the abyssopelagic zone, extending from roughly 4,000 to 6,000 meters. This region covers vast areas of the ocean floor and represents one of the least explored environments on Earth. Conditions here are remarkably stable. Temperatures are consistently low, and there is no seasonal variation in light or surface influence. Life exists at low densities, and organisms often grow slowly, conserving energy in an environment where resources are limited. Finally, in the deepest parts of the ocean, we find the Hadal zone, which includes trenches deeper than 6,000 meters. These regions are found in only a few locations around the world, but they represent the most extreme marine environments known. Pressure in the Hadal zone is immense, more than 1,000 times atmospheric pressure at the surface. Yet even here life has been discovered. Small crustaceans, microorganisms, and other specialized species have adapted to survive under these conditions, often feeding on organic material that accumulates in trench floors. The vertical structure of the ocean is not static. Water moves slowly between layers through processes such as mixing, sinking, and upwelling. Cold, dense water formed near the poles can sink and travel through the deep ocean for centuries before rising again elsewhere. This global circulation helps regulate temperature, distribute nutrients, and stabilize Earth's climate over long time scales. Understanding the ocean vertically reveals how connected its layers truly are. Surface processes influence deep environments, and deep circulation patterns affect surface conditions. What happens near the top does not stay there. It moves downward, sometimes slowly, sometimes invisibly, shaping the entire system. As we continue this journey, depth will become more than a measurement. It will begin to shape how we understand pressure, time, and adaptation in the ocean, leading us naturally toward the forces that operate in the deep and the life that responds to them. The ocean is often perceived as a vast, still body of water, especially when observed from above. Yet beneath the surface and across immense distances, the ocean is constantly in motion. This movement does not usually resemble waves or turbulence. Instead, it unfolds slowly, steadily, and with remarkable persistence. Ocean currents form one of the most important systems regulating Earth's climate, distributing heat, nutrients, and life across the planet. Ocean currents can be understood as large-scale pathways along which water moves. Some currents are driven primarily by wind at the surface, while others are shaped by differences in temperature, salinity, and density at depth. Together, these movements form a global circulation system that connects all the world's oceans into a single interdependent system. Surface currents are the most visible and familiar. They are largely driven by prevailing winds and influenced by Earth's rotation through the Coriolis effect. This causes moving water to curve rather than travel in straight lines, creating large rotating systems known as gyres. There are 5 major ocean gyres: in the North and South Atlantic, the North and South Pacific, and the Indian Ocean. Within these gyres, warm water is typically transported away from the equator along western boundaries, while cooler water flows toward the equator along eastern boundaries. This pattern helps redistribute heat from regions of high solar input to cooler latitudes. One of the most well-known surface currents is the Gulf Stream. Originating in the Gulf of Mexico, it carries warm water northward along the eastern coast of North America and across the Atlantic toward Europe. This current plays a significant role in moderating the climate of Western Europe, making it much warmer than other regions at similar latitudes. Surface currents also influence marine ecosystems. By moving water masses, they transport plankton, larvae, and nutrients across vast distances. This connectivity allows species to disperse and ecosystems to remain productive, even in areas where local conditions might otherwise be limiting. Below the surface, however, a different kind of movement dominates, one that is slower, deeper, and far less visible. This is known as thermohaline circulation, a process driven by differences in temperature, thermo, and salinity, haline. Cold, salty water is denser than warm, fresh water. In certain regions of the world, particularly near the poles, surface water becomes colder and saltier due to cooling and ice formation. As sea ice forms, salt is left behind in the surrounding water, increasing its density. This dense water sinks, initiating deep currents that travel through the ocean's depths. Once formed, deep water masses can move slowly across entire ocean basins. Some of this water may take hundreds or even thousands of years to complete a full circuit before returning to the surface. This slow movement is often described as the global conveyor belt. The global conveyor belt links the Atlantic, Pacific, and Indian Oceans into a continuous system. It plays a crucial role in stabilizing Earth's climate by transporting heat and storing carbon in the deep ocean for long periods. Without this system, temperature differences between regions would be far more extreme. Unlike surface currents, deep currents are not influenced by wind. They are shaped by the contours of the ocean floor, moving along slopes, basins, and ridges. The shape of the seafloor channels these currents, guiding their paths over long distances. Where deep currents eventually rise back toward the surface, a process known as upwelling, nutrient-rich water is brought into sunlight zones. This supports high levels of biological productivity. Some of the world's most productive fisheries are found in upwelling regions, where cold, nutrient-dense water fuels plankton growth. Upwelling also helps connect deep ocean processes with surface ecosystems. Materials that have been stored in the deep ocean for centuries can re-enter biological cycles, influencing food webs and atmospheric chemistry. Ocean currents do not operate in isolation. They interact continuously with the atmosphere. Winds drive surface currents, while ocean temperatures influence wind patterns, storm formation, and precipitation. This interaction forms the basis of many climate phenomena. One example is El Niño, a periodic disruption of normal ocean circulation in the Pacific. During El Niño events, warm surface water spreads eastward, altering weather patterns across the globe. These changes can bring heavy rains to some regions and droughts to others, illustrating how ocean movement affects life far beyond the sea. Over long timescales, changes in ocean circulation have been linked to shifts in climate. Evidence from ice cores and marine sediments suggests that alterations in deep ocean currents have coincided with periods of warming and cooling in Earth's history. Despite their importance, ocean currents often move at speeds that feel almost imperceptible. Deep currents may travel only a few centimeters per second. Yet given enough time, this steady motion reshapes the planet's energy balance. This slowness is a defining feature of ocean circulation. Unlike the rapid movements seen in the atmosphere, the ocean operates on longer rhythms. Its changes unfold over decades, centuries, and millennia. This temporal scale provides stability, buffering Earth against sudden climatic shifts. The movement of water also influences how sound, nutrients, and even pollutants travel through the ocean. Materials introduced at the surface may eventually reach the depths, while substances released in deep waters can slowly disperse across vast areas. Understanding ocean currents reveals the ocean as an active, living system, one that connects distant regions and balances extremes. Nothing in the ocean is truly isolated. Every current is part of a larger flow, linking surface and depth, tropics and poles, present conditions, and long-term stability. As we move forward, this understanding of movement prepares us to explore how the ocean shapes climate more directly and how its steady circulation influences the conditions under which life has evolved, both in the sea and on land. Life in the ocean does not spread evenly across its vast expanse. Instead, it follows patterns shaped by light, pressure, temperature, chemistry, and time. From the sunlit surface to the deepest trenches, life adapts to conditions that change gradually but relentlessly with depth. Understanding how marine life is distributed reveals how the ocean functions as a living system rather than a uniform environment. The ocean can be divided into vertical life zones, each defined primarily by the availability of light. The epipelagic zone, also known as the sunlight zone, extends from the surface to about 200 meters deep. This is where sunlight penetrates strongly enough to support photosynthesis. As a result, this relatively thin layer hosts the majority of visible marine life. Phytoplankton form the foundation of oceanic food webs in this zone. These microscopic organisms use sunlight to convert carbon dioxide into organic matter, producing oxygen in the process. Despite their small size, phytoplankton collectively generate a significant portion of Earth's oxygen and support nearly all marine ecosystems, directly or indirectly. Above them move zooplankton, fish, marine mammals, and seabirds, forming complex food chains. Many species here rely on vision, color, and speed, adaptations suited to a bright, dynamic environment shaped by waves, currents, and seasonal change. Below the epipelagic zone lies the mesopelagic, or twilight zone, extending from about 200 to 1,000 meters. Light here is faint and insufficient for photosynthesis. This region marks a profound shift in biological strategy. Life continues, but it adapts to darkness, lower temperatures, and increasing pressure. Many organisms in the twilight zone exhibit bioluminescence, producing their own light through chemical reactions. This light serves various functions: attracting prey, confusing predators, or communicating with others of the same species. In the absence of sunlight, light becomes a tool shaped by evolution. The mesopelagic zone hosts one of the largest daily migrations on Earth. Each night, billions of organisms rise toward the surface to feed, then descend again before dawn. This vertical movement plays a major role in transporting carbon from the surface to deeper waters, linking biological activity to global carbon cycles. Below this lies the bathypelagic zone, where darkness is complete. Temperatures are cold, pressure is immense, and food is scarce. Life here relies on organic material sinking from above, or on localized sources such as hydrothermal vents. Organisms in this zone exhibit slow metabolisms, reduced musculature, and specialized feeding strategies. Many have soft bodies that withstand pressure, while others possess expandable stomachs, allowing them to consume rare meals when opportunities arise. Deeper still, the abyssopelagic and hadal zones represent some of the most extreme environments on Earth. These regions include abyssal plains and deep ocean trenches, where pressure can exceed 1,000 times that at the surface. Life persists even here. Bacteria, invertebrates, and specialized fish species have adapted at the molecular level. Their proteins, cell membranes, and enzymes function under conditions that would destroy most surface organisms. These adaptations illustrate that life does not merely tolerate the ocean's extremes, it is shaped by them. One of the most remarkable discoveries of modern oceanography is that life in the deep ocean does not depend entirely on sunlight. At hydrothermal vents, entire ecosystems thrive on chemosynthesis, using chemical energy rather than light. Here, bacteria convert minerals from Earth's interior into usable energy, forming the base of food webs independent of the surface world. These ecosystems challenge earlier assumptions that sunlight was essential for life and expand our understanding of where life might exist elsewhere in the universe. Across all depths, marine life shows a tendency toward efficiency and conservation. Energy is rarely wasted. Movements are deliberate. Growth is often slow. Reproduction strategies favor survival over abundance. These traits reflect the ocean's long timescales and limited resources. Marine organisms also play a crucial role in regulating Earth's systems. Through respiration, photosynthesis, and the sinking of organic matter, ocean life influences atmospheric composition and climate stability. The ocean acts as both a reservoir and a processor of carbon, with life serving as an essential intermediary. Importantly, the ocean is not divided into isolated biological layers. Species, nutrients, and energy move between zones through migration, sinking particles, and currents. This connectivity ensures that even the deepest ecosystems remain linked to surface processes, however indirectly. Human activity increasingly intersects with these delicate systems. Fishing, pollution, and climate change affect not only surface species, but also deep-sea communities that recover slowly from disturbance. Understanding how life is distributed and adapted helps clarify why many oceanic impacts unfold gradually and persist long after initial disruption. The ocean's living structure reflects patience and continuity. Life does not rush here. It adapts incrementally, responding to pressure, scarcity, and darkness with persistence rather than speed. These patterns mirror the broader rhythms of the ocean itself, steady, layered, and deeply interconnected. As we move forward, this understanding of life prepares us to explore how the ocean influences Earth's climate more directly, and how biological processes interact with physical systems to maintain balance across vast scales of time. The oceans are not passive bodies of water resting between continents. They are active regulators of Earth's climate, shaping temperatures, weather patterns, atmospheric composition, and long-term planetary stability. Their influence unfolds slowly, often invisibly, but with consequences that extend across centuries and millennia. More than 70% of Earth's surface is covered by ocean water. This vast coverage gives the oceans an unmatched capacity to absorb, store, and redistribute heat. Water warms and cools more slowly than land, allowing the oceans to act as thermal buffers that reduce extreme temperature fluctuations across the planet. During periods of warming, the oceans absorb excess heat from the atmosphere. During cooler periods, they release stored warmth back into the air. This exchange moderates climate variability and helps stabilize conditions necessary for life on land and at sea. Ocean currents play a central role in this process. Driven by wind, Earth's rotation, differences in temperature, and variations in salinity, currents transport heat from equatorial regions toward higher latitudes. Warm surface currents carry energy poleward, while cold deep currents return cooler water toward the equator. One of the most well-known examples is the global thermohaline circulation, sometimes referred to as the ocean's conveyor belt. This interconnected system of surface and deep currents moves water slowly around the globe, completing a full cycle over roughly 1,000 years. In this system, warm surface water travels northward in the Atlantic, gradually cooling and increasing in density. As it becomes colder and saltier, it sinks into the deep ocean and flows southward, eventually rising again in other regions. This slow circulation redistributes heat, oxygen, nutrients, and carbon throughout the ocean. The influence of this circulation extends far beyond the sea. For example, it helps keep parts of Western Europe significantly warmer than other regions at similar latitudes. Without this ocean-driven heat transport, global climate patterns would look very different. In addition to heat, the oceans play a critical role in regulating atmospheric gases. They absorb approximately a quarter of the carbon dioxide released into the atmosphere each year by natural processes and human activities. This absorption slows the pace of climate change, acting as a temporary buffer against rising greenhouse gas concentrations. Carbon enters the ocean in several ways. Some dissolves directly into surface waters. Some is taken up by phytoplankton through photosynthesis. When these organisms die or are consumed, carbon-rich material sinks toward deeper layers, a process known as the biological carbon pump. This slow downward movement transfers carbon from the surface to the deep ocean, where it can remain stored for hundreds or even thousands of years. In this way, the ocean acts as a long-term reservoir, moderating atmospheric carbon levels across geological timescales. However, this buffering capacity is not unlimited. As more carbon dioxide dissolves into seawater, it alters ocean chemistry, leading to ocean acidification. This gradual change reduces the availability of carbonate ions, which many marine organisms rely on to build shells and skeletons. These chemical shifts occur quietly and incrementally, yet they can influence entire ecosystems. Coral reefs, shellfish, and plankton species are particularly sensitive to changes in ocean acidity, highlighting how tightly climate, chemistry, and life are linked. The oceans also regulate climate through their interaction with the water cycle. Evaporation from the ocean surface supplies most of the moisture in Earth's atmosphere. This moisture later falls as precipitation, shaping weather patterns, freshwater availability, and ecosystem productivity across continents. Large-scale climate phenomena such as El Niño and La Niña emerge from changes in ocean temperature and circulation. These events alter wind patterns and rainfall distribution on a global scale, affecting agriculture, ecosystems, and economies far from the ocean itself. Despite their power, ocean-driven climate processes operate slowly. Changes often unfold over decades or centuries rather than days or years. This slow pace can make them difficult to perceive, yet it also gives the climate system a form of inertia, resistance to rapid shifts. At the same time, this inertia means that disruptions once initiated can persist long after their causes are removed. Heat absorbed today may remain stored in the deep ocean for generations, influencing future climate conditions long after surface temperatures stabilize. The deep ocean plays a particularly important role in this long-term regulation. Cold, dense waters sink and spread across abyssal plains, carrying with them heat and dissolved gases. These deep reservoirs exchange very slowly with the surface, acting as memory layers within the climate system. Understanding this vertical structure helps explain why climate change is not a surface-only phenomenon. Even as surface conditions fluctuate, deeper layers continue absorbing heat and carbon, quietly reshaping the planet's energy balance. From a planetary perspective, the oceans function as a stabilizing force. They reduce extremes, distribute resources, and smooth transitions. Without them, Earth's climate would be harsher, more variable, and less hospitable to complex life. Yet this stability depends on delicate balances. Changes in temperature, circulation, or chemistry can alter how effectively the oceans perform their regulatory role. Because these processes are interconnected, small shifts can propagate slowly but widely through the system. As we continue, this understanding of the ocean's climatic role prepares us to look more closely at how humans interact with these systems and how modern activity intersects with processes shaped over millions of years. Life in the oceans is organized not only across distances, but across depth. From the sunlit surface to the silent abyss, each vertical layer of the ocean hosts distinct forms of life, shaped by light, pressure, temperature, and the slow movement of water. At the surface lies the photic zone, the upper layer where sunlight penetrates the water. This zone, though relatively thin compared to the ocean's total depth, supports the majority of marine life. Here light enables photosynthesis, allowing microscopic organisms called phytoplankton to convert sunlight into energy. Phytoplankton form the foundation of the oceanic food web. Despite their small size, they produce roughly half of the oxygen in Earth's atmosphere and support nearly all marine ecosystems, directly or indirectly. Their presence links ocean life to atmospheric processes and to life on land. Floating, drifting, and swimming organisms populate this illuminated layer. Fish, jellyfish, marine mammals, and countless invertebrates rely on the productivity generated at the surface. Seasonal changes in light, temperature, and nutrient availability influence migrations, breeding cycles, and feeding patterns. Below the photic zone lies the twilight zone, also known as the mesopelagic zone. Here, sunlight fades rapidly, and photosynthesis becomes impossible. Yet, life continues, adapted to dim conditions and limited energy. Many organisms in this zone rely on organic material sinking from above. This slow rain of particles, sometimes called marine snow, consists of dead plankton, fecal matter, and organic debris. Though sparse, it provides a steady energy source for deep-dwelling species. Creatures of the twilight zone often display specialized adaptations. Large eyes, slow metabolisms, and bioluminescence are common. Light is no longer abundant, but it is still used for communication, camouflage, and attraction. Deeper still lies the midnight zone, where sunlight disappears entirely. Temperatures are low, pressure is immense, and food is scarce. Yet life persists, shaped by extreme conditions rather than abundance. Fish, crustaceans, and soft-bodied organisms here tend to move slowly, conserving energy. Many have flexible bodies and reduced skeletal structures to withstand pressure. Some rely on chemosynthesis rather than photosynthesis, drawing energy from chemical reactions rather than sunlight. At the deepest levels, the abyssal and hadal zones, life exists under conditions once thought impossible. Trenches plunge kilometers below the surface, creating isolated environments where pressure can exceed 1,000 times that at sea level. Despite these extremes, organisms such as amphipods, worms, and specialized microbes thrive. Their existence demonstrates that life does not require light, warmth, or familiarity, only stability and time to adapt. Across all depths, ocean life is interconnected. Surface productivity supports deep ecosystems. Deep circulation returns nutrients upward over centuries. Vertical migrations link layers daily as organisms move up to feed at night and descend again by day. This vertical movement is one of the largest migrations on Earth by biomass, occurring invisibly each night across the global ocean. It redistributes nutrients, carbon, and energy between layers, reinforcing the ocean's role as an integrated system. Marine life also shapes the physical and chemical properties of the ocean. Through respiration, growth, and decay, organisms influence oxygen levels, carbon storage, and nutrient cycling. Life does not simply exist within the ocean, it actively participates in its regulation. Biodiversity in the ocean is immense, yet unevenly distributed. Coral reefs, coastal zones, and upwelling regions host high concentrations of species, while vast open ocean areas contain life spread thinly over great distances. Both patterns reflect the availability of energy and nutrients. Importantly, much of ocean life remains undocumented. New species are regularly discovered, particularly in deep-sea environments. Each discovery expands our understanding of how life adapts, persists, and evolves under conditions vastly different from those on land. The slow pace of deep ocean ecosystems contrasts with the more dynamic surface. Changes in deep communities unfold over long timescales, often measured in centuries. This slowness contributes to their stability, but also to their vulnerability. Disturbances introduced at the surface, such as warming waters, acidification, or changes in nutrient flow, can eventually propagate downward, affecting ecosystems that evolved under relatively constant conditions. Understanding life in the oceans requires seeing depth not as emptiness, but as structure. Each layer forms part of a continuous vertical system where energy, matter, and organisms move gradually, linking the surface world to the deepest trenches. As we move forward, this layered view of ocean life prepares us to examine how human activity intersects with these systems and how modern influences reach even the most remote depths. The oceans are never truly still. Beneath their calm surfaces, vast movements unfold continuously, shaping climate, distributing life, and connecting distant regions of the planet. These movements are known as ocean currents, and they form the moving architecture of the seas. Ocean currents are large-scale flows of seawater driven by a combination of wind, Earth's rotation, differences in temperature, and variations in salinity. Together, these forces create a global circulation system that operates across both the surface and the depths. At the surface, currents are primarily driven by wind patterns. As wind moves across the ocean, friction transfers energy to the water, setting it in motion. Over time, these movements organize into persistent current systems that follow predictable paths. Earth's rotation influences these flows through the Coriolis effect, which causes moving water to curve to the right in the northern hemisphere and to the left in the southern hemisphere. This deflection shapes the large circular systems known as gyres. 5 major ocean gyres dominate the global surface circulation, 2 in the Atlantic, 2 in the Pacific, and 1 in the Indian Ocean. Within these gyres, water moves slowly but steadily, completing circuits that can take years or even decades. Some currents transport warm water from equatorial regions toward higher latitudes. Others carry cold water from polar regions toward the tropics. This redistribution of heat plays a crucial role in regulating Earth's climate. For example, the Gulf Stream carries warm water from the Gulf of Mexico across the North Atlantic, moderating temperatures in Western Europe. Without this current, regional climates would be significantly colder. In contrast, cold currents such as the California Current or the Humboldt Current bring nutrient-rich waters to the surface. These upwelling zones support some of the most productive marine ecosystems on Earth. Upwelling occurs when surface waters are pushed away by wind, allowing deeper water to rise. This deeper water is rich in nutrients accumulated from sinking organic material. When it reaches the surface, It fuels plankton growth, which supports entire food webs. Beyond surface currents lies a slower but far-reaching system known as thermohaline circulation. This deep ocean circulation is driven by differences in water density, which depend on temperature and salinity. Cold, salty water is denser than warm, fresh water. In polar regions, seawater cools and becomes saltier as ice forms, increasing its density. This dense water sinks and begins a slow journey through the deep ocean. Once submerged, deep currents move gradually along the ocean floor, flowing across basins and between continents. Over centuries, this water eventually rises back toward the surface in other regions, completing a global loop often called the global conveyor belt. This circulation links all major oceans into a single system. Water that sinks in the North Atlantic may eventually resurface in the Pacific or Indian Ocean thousands of years later. Time in this context is measured on geological scales rather than human ones. Ocean currents influence not only climate, but also chemistry. They transport oxygen to deep waters and help regulate carbon storage. Through these processes, the oceans act as a major buffer against rapid climate change. Currents also shape the distribution of marine life. Many species rely on currents to disperse larvae, migrate, or access feeding grounds. Floating organisms travel vast distances without active movement, carried by the slow motion of water. Even at depth, currents exist. Though slower and less visible, deep currents sculpt the seafloor, transport sediments, and maintain the chemical balance of abyssal environments. These movements sustain life in regions far removed from sunlight. Importantly, ocean circulation is not fixed. It responds to changes in temperature, ice cover, and freshwater input. Shifts in circulation patterns can have wide-ranging effects, influencing weather systems, ecosystems, and long-term climate stability. Today, scientists monitor currents using satellites, drifting instruments, and deep-sea sensors. These observations help us understand how the ocean responds to ongoing environmental change and how resilient these circulation systems may be. Despite their scale, currents move with remarkable steadiness. Their pace is measured not in moments but in years and centuries. This slow movement contributes to the ocean's stabilizing influence on the planet. As water flows continuously through surface and deep pathways, it connects distant regions into a single dynamic system. Nothing in the ocean exists in isolation. Each movement participates in a broader circulation that sustains life and climate alike. Understanding ocean currents allows us to see the sea not as a static body, but as a living system in motion, quiet, persistent, and deeply interconnected. This awareness prepares us to explore how oceans interact with the atmosphere above them, shaping weather, climate patterns, and the rhythms experienced on land. The surface of the ocean is in constant motion. Even when it appears calm, energy is always passing through it. Waves rise and fall, tides advance and retreat, and long oscillations move across entire basins. These movements form the rhythms of the ocean, repeating patterns that connect the sea to the moon, the wind, and the rotation of Earth itself. Waves are the most visible expression of ocean motion. They are created primarily by wind transferring energy to the surface of the water. As wind blows across the ocean, it creates friction, pushing the water into motion. The longer the wind blows, the stronger it is, and the greater the distance it travels over open water, the larger the waves become. Importantly, waves are not the forward movement of water itself. Instead, they are the movement of energy passing through the water. Individual water particles move in small circular paths, rising and falling as the wave passes, then returning to roughly the same position. Energy travels. The water largely stays in place. This distinction allows waves to cross vast distances. Swells generated by distant storms can travel thousands of kilometers across open oceans, arriving at coastlines days later with no visible connection to the weather that created them. As waves approach shallow water near land, their behavior changes. The lower part of the wave begins to interact with the seafloor, slowing down while the upper part continues moving forward. This causes waves to increase in height and eventually break, releasing their energy along coastlines. This process plays a major role in shaping shores. Over long periods, waves erode cliffs, transport sediments, and build beaches. Coastlines are not fixed boundaries. They are continually reshaped by the steady arrival of wave energy. Beyond wind-driven waves, the ocean also experiences tides, which operate on a much larger scale and follow a precise, predictable rhythm. Tides are caused primarily by the gravitational interaction between Earth, the Moon, and the Sun. The Moon exerts the strongest tidal influence due to its proximity. Its gravitational pull causes the ocean to bulge slightly toward the Moon. At the same time, a second bulge forms on the opposite side of Earth due to inertia. As Earth rotates, different regions move through these bulges, creating cycles of rising and falling sea levels. Most coastlines experience 2 high tides and 2 low tides each day, a pattern known as semi-diurnal tides. In some regions, tides follow different patterns depending on geography and basin shape. The sun also contributes to tidal forces. When the sun, moon, and earth align during new and full moons, their gravitational forces combine, producing spring tides, which have a greater range between high and low water. When the sun and moon are at right angles relative to Earth, neap tides occur, producing smaller tidal ranges. Tides influence far more than coastlines. They drive the mixing of water in shallow seas, transport nutrients, and affect the behavior of countless marine organisms. Many species time feeding, spawning, and migration, with tidal cycles that have remained stable for millions of years. In estuaries where rivers meet the sea, tides interact with freshwater flow, creating dynamic environments with shifting salinity and strong nutrient exchange. These areas are among the most productive ecosystems on the planet. Beyond daily tides, the ocean also experiences longer period oscillations. Some are linked to seasonal wind patterns, while others result from basin-wide interactions between atmosphere and ocean. These slower rhythms influence water levels, temperature distribution, and biological productivity over months or years. Though subtle, they shape the long-term character of entire ocean regions. Importantly, ocean rhythms are interconnected. Waves respond to wind, tides respond to gravity, and both interact with currents, seafloor shape, and coastal geometry. No single motion exists in isolation. Even in the deep ocean, far below the reach of surface waves, pressure variations caused by tides can be detected. The influence of the moon reaches all the way to the ocean floor, reminding us that even the most remote environments remain connected to celestial mechanics. For human societies, ocean rhythms have always been significant. Coastal navigation, fishing practices, and settlement patterns developed around predictable tidal cycles. Long before modern instruments existed, people learned to read the timing of the sea. Today, these rhythms are monitored with precision using satellites, tide gauges, and ocean sensors. This data helps scientists understand sea level change, coastal vulnerability, and the response of ocean systems to a warming climate. Despite these technological advances, the fundamental patterns remain unchanged. Waves still rise and fall as they have for ages. Tides continue their steady cycles, guided by forces far beyond human control. There is a quiet reliability in these movements. They repeat without urgency, following rhythms that do not accelerate or pause. This steadiness contributes to the ocean's calming presence. To observe waves and tides is to witness time expressed through motion, not as sudden change, but as repetition and flow. The ocean does not rush. It moves according to patterns established long before memory. As we become familiar with these surface rhythms, we are ready to look beneath them, into the vertical structure of the ocean, where light, pressure, and depth shape very different environments. Beneath the visible movement of waves and tides, the ocean is organized by vast systems of motion known as ocean currents. These currents form a global circulation that moves water, heat, nutrients, and energy across the planet. They operate on timescales ranging from days to centuries, shaping climate, ecosystems, and the conditions for life both in the sea and on land. Ocean currents are not random. They follow physical laws governed by wind, Earth's rotation, differences in temperature and salinity, and the shape of ocean basins. Together, these forces create a slow but persistent movement of water that connects distant regions of the world. At the surface, currents are driven primarily by wind patterns. Persistent winds, such as trade winds and westerlies, push surface waters across the ocean. As water moves, it is deflected by Earth's rotation through a process known as the Coriolis effect, causing currents to curve rather than flow in straight lines. In the northern hemisphere, this deflection causes surface currents to rotate clockwise around ocean basins. In the southern hemisphere, they rotate counterclockwise. These rotating systems are called gyres, and they dominate the circulation of the major oceans. Each major ocean basin contains large gyres that move warm water from the equator toward higher latitudes and return cooler water back toward the tropics. This circulation helps redistribute heat around the planet, moderating temperature differences between regions. One of the most well-known surface currents is the Gulf Stream, which carries warm water from the Gulf of Mexico across the North Atlantic toward Europe. This current plays a significant role in keeping parts of Western Europe warmer than other regions at similar latitudes. Surface currents also influence marine life. They transport plankton, larvae, and nutrients across large distances, shaping the distribution of species. Many marine organisms rely on these currents during early life stages, drifting with them before settling into specific habitats. While surface currents are driven mainly by wind, the deep ocean follows a different system of movement known as thermohaline circulation. This circulation is driven by differences in water density, which depend on temperature, thermo, and salinity, haline. Cold, salty water is denser than warm, fresh water. In certain regions, especially near the poles, surface water becomes cold enough and salty enough due to ice formation to sink into the deep ocean. This sinking water begins a slow journey along the ocean floor. Once submerged, deep water flows through ocean basins, guided by underwater topography such as ridges, trenches, and continental slopes. Over hundreds to thousands of years, this water gradually rises back toward the surface in other regions, completing a global loop. This deep circulation is often described as a global conveyor belt, though it is not a single current, but a complex network of interconnected flows. Despite its slow pace, this system plays a critical role in regulating Earth's climate by storing and transporting heat and carbon. The deep ocean acts as a vast reservoir. It absorbs large amounts of heat and carbon dioxide from the atmosphere, slowing the pace of climate change. Changes to thermohaline circulation can have long-lasting effects on global climate patterns. Currents also influence oxygen distribution in the ocean. As surface water sinks, it carries dissolved oxygen into the deep sea, supporting life in environments far removed from direct contact with the atmosphere. In regions where deep water rises to the surface, a process known as upwelling occurs. Upwelling brings cold, nutrient-rich water from the depths into sunlit surface layers. These nutrients fuel the growth of phytoplankton, forming the base of productive marine food webs. Some of the world's most important fishing regions are associated with upwelling zones, where currents and winds work together to sustain high biological productivity. Ocean currents are shaped by the structure of the seafloor. Mid-ocean ridges, submarine plateaus, and continental margins redirect flows, creating complex pathways. Even small changes in seafloor topography can influence current behavior over large areas. Although currents are steady on human timescales, they are not fixed. Seasonal changes in wind patterns, freshwater input from rivers, and melting ice can alter their strength and direction. Over longer periods, shifts in climate can reorganize entire circulation systems. Scientists study ocean currents using satellites, drifting instruments, underwater sensors, and numerical models. These tools reveal patterns that were once invisible, showing the ocean as a dynamic, interconnected system rather than a static body of water. Despite this complexity, there is a sense of continuity in ocean circulation. Currents follow pathways established by Earth's rotation, gravity, and geometry, forces that change slowly, if at all. From the surface to the deepest layers, ocean water is always moving, though often at speeds too slow to be noticed. This quiet movement forms the background rhythm of the planet, operating steadily without pause. To understand ocean currents is to understand how the planet breathes heat and energy across vast distances. It is a reminder that no ocean region exists alone. Each is part of a larger system that connects poles to equator, surface to depth. As we move forward, This circulation leads us naturally to consider how the ocean is layered vertically, how light, pressure, and temperature divide the sea into distinct zones, each with its own conditions and forms of life. The oceans are not only vast bodies of water covering most of the Earth's surface, they are active regulators of the planet's systems, quietly shaping climate, chemistry, and life itself. From the movement of heat around the globe to the balance of gases in the atmosphere, oceans operate as a stabilizing force. Their influence is constant, patient, and largely unseen. Yet without it, the planet would behave very differently. One of the most important roles of the oceans is heat regulation. Water absorbs and stores heat far more efficiently than land. During the day and across seasons, the oceans take in enormous amounts of solar energy, releasing it slowly over time. This process softens temperature extremes, preventing the planet from overheating during warm periods and from cooling too rapidly during colder ones. Ocean currents act as moving conveyors of this stored heat. Warm surface currents transport energy from equatorial regions toward higher latitudes, while colder currents return cooler water toward the tropics. This circulation helps maintain relatively stable climates in many coastal regions. Without it, some areas would be far colder, while others would become dangerously hot. The oceans also play a crucial role in atmospheric balance. A significant portion of the oxygen in the air originates from marine photosynthesis, primarily carried out by microscopic organisms such as phytoplankton. These tiny life forms drift near the surface, converting sunlight, carbon dioxide, and nutrients into organic matter and oxygen. Though invisible to the naked eye, they collectively contribute roughly half of the oxygen produced on Earth. At the same time, the oceans absorb large quantities of carbon dioxide from the atmosphere. This process helps regulate greenhouse gas concentrations and slows the pace of climate change. Carbon moves between air and sea through constant exchange, dissolving into surface waters and, over time, being transported into deeper layers. This slow movement of carbon into the deep ocean acts as a long-term storage system, sometimes holding carbon for hundreds or even thousands of years. It is a quiet, buffering process, not dramatic, not immediate, but profoundly important for planetary stability. Another regulatory function lies in the water cycle. Oceans are the primary source of atmospheric moisture. Through evaporation, vast quantities of water rise into the air, later condensing into clouds and falling as precipitation across the continents. Rain, snow, and ice that nourish rivers, forests, and soils ultimately trace their origins back to the sea. This cycle links distant landscapes. Water evaporated from tropical oceans may fall as snow in mountain ranges thousands of kilometers away. Rivers then carry that water back toward the oceans, completing a slow, continuous loop that has persisted for millions of years. The oceans also regulate chemical balance. Seawater contains a complex mixture of dissolved salts and minerals that remain remarkably stable over geological time. This chemical consistency supports marine life and influences processes such as shell formation, nutrient cycling, and biological growth. Deep ocean circulation contributes to this stability. Cold, dense water sinks in polar regions and flows slowly along the ocean floor, eventually rising elsewhere. This movement distributes oxygen, nutrients, and dissolved compounds throughout the global ocean, preventing stagnation and maintaining long-term balance. Importantly, these regulating processes do not operate quickly. Ocean systems function on timescales far longer than human attention usually allows. Some currents take centuries to complete a full circuit. Deep waters may not see the surface again for 1,000 years or more. This slowness is not a flaw. It is part of the ocean's stabilizing nature. While weather can change in hours and land temperatures can shift rapidly, the oceans resist sudden transformation. They absorb shocks, distribute energy gradually, and soften extremes. For human observers, this creates a particular experience. Standing near the ocean often brings a sense of calm, not because the sea is always still, but because it moves according to rhythms far larger than immediate concerns. Waves rise and fall, tides advance and retreat, currents flow steadily beneath the surface, all without urgency. In this way, oceans shape not only the planet's systems, but also human perception. They offer a physical example of regulation through patience rather than force. As we continue exploring the oceans, it becomes clear that their role is not simply to host life, but to hold the planet in balance, thermally, chemically, and biologically. This balance is not static. It is dynamic, continuously adjusting, yet remarkably resilient. And it is within this quiet regulation that the next layer of ocean life unfolds, where ecosystems depend on stability to exist at all, and where even the smallest changes ripple slowly through vast, interconnected systems. Before moving forward, take a moment to notice the pace of your own breathing. Like the oceans, it does not need to hurry. It moves, adjusts, and continues, steady, reliable, and quietly sustaining. Beyond the coastlines and continental shelves lies the open ocean, a vast, seemingly uniform expanse that in reality is highly structured. Life in this environment does not spread randomly. It organizes itself according to depth, light, temperature, nutrients, and movement. These invisible layers and patterns shape one of the most extensive ecosystems on Earth. Unlike forests or reefs, the open ocean has few fixed landmarks. There are no trees, rocks, or stable surfaces for most organisms to attach to. Instead, life here depends on motion, of water, of light, of chemical gradients. This constant movement creates distinct biological zones, each supporting different forms of life. The most influential factor is light. Sunlight penetrates only the upper portion of the ocean, forming the photic zone, which typically extends down about 200 meters. This is where photosynthesis occurs, making it the foundation of nearly all marine food webs. Within this sunlit layer, microscopic phytoplankton convert light and nutrients into organic matter. Though individually tiny, they exist in such vast numbers that they form the base of ocean productivity. Zooplankton feed on phytoplankton, small fish feed on zooplankton, and larger predators feed on them in turn. This layered transfer of energy supports life far beyond the surface. Below the photic zone lies the twilight zone, where light fades rapidly. Photosynthesis is no longer possible, yet life remains abundant. Many organisms here rely on organic material drifting down from above, a slow rain of particles known as marine snow, composed of dead plankton, waste, and microscopic debris. Life in this dim region often displays remarkable adaptations. Many species have large eyes to capture faint light, elongated bodies to conserve energy, and slow metabolisms suited to scarce food. Movement becomes deliberate rather than rapid, reflecting the limited energy available. Deeper still, beyond the reach of light, lies the midnight zone and the deep ocean below. Here, temperatures are cold, pressure is immense, and food is scarce. Yet life persists. Organisms survive by efficiency rather than abundance, often feeding infrequently and growing slowly over long lifespans. One of the most striking patterns in the open ocean is vertical migration. Each day, countless organisms move upward at night and downward during daylight hours. This daily rhythm, known as the largest migration on Earth by biomass, helps animals feed in surface waters while avoiding predators during daylight. This movement also plays a role in global carbon cycling. As organisms consume carbon-rich food near the surface and release waste at depth, they transport carbon downward, contributing to long-term storage in the deep ocean. Once again, biological activity quietly supports planetary balance. Horizontal patterns are equally important. Ocean currents concentrate nutrients, plankton, and life into dynamic regions such as fronts, eddies, and upwelling zones. These areas often appear featureless from above, yet they function as biological hotspots, supporting fish, seabirds, and marine mammals. In the open ocean, nutrients often limit life more than space. Regions with abundant sunlight but low nutrients, such as subtropical gyres, appear biologically sparse despite their size. Conversely, areas where deep water rises to the surface bring nutrients upward, fueling productivity even in relatively small zones. These patterns are not static. They shift with seasons, climate cycles, and long-term ocean circulation. Life responds not by resisting change, but by adjusting distribution, timing, and behavior. Flexibility rather than permanence defines survival in the open ocean. For humans, observing from the surface, the open ocean may seem empty, yet beneath that surface lies a layered, moving system where life is finely tuned to physical conditions. Every depth, current, and temperature boundary shapes who can live there and how they survive. This organization creates a sense of quiet order. Nothing rushes. Nothing accumulates excessively. Energy flows, transforms, and disperses gradually. Even predation often follows patterns of patience rather than speed, reflecting the broader rhythm of the environment. In this way, the open ocean offers a different model of abundance, one not based on density or visibility, but on balance and continuity. Life does not crowd the space, it spreads thinly, efficiently, and persistently across immense distances. As you listen, imagine these layers unfolding gently beneath the surface, light softening into shadow, movement slowing as depth increases, life adapting not through force, but through precision and restraint. These patterns prepare us to look deeper still, toward environments where life survives under conditions once thought impossible, and where the ocean reveals yet another dimension of its quiet complexity. When night arrives over the ocean, the change is gradual rather than abrupt. Light fades slowly from the surface, colors soften, and the boundary between sky and water becomes less defined. Unlike land, where darkness often brings stillness, the ocean enters a different phase of activity, one shaped by temperature shifts, biological rhythms, and subtle movements. The most immediate change is the loss of sunlight. As the sun sinks below the horizon, the surface layer of the ocean begins to cool. This cooling increases the density of surface water, causing it to sink slightly and mix with the layers below. Even this gentle process plays a role in redistributing heat and nutrients, continuing cycles that operate quietly every night. For many marine organisms, nightfall signals movement rather than rest. In the open ocean, countless animals begin their daily vertical migration. Zooplankton, small fish, and other organisms rise toward the surface under the cover of darkness, feeding in nutrient-rich waters that were too exposed during daylight hours. This behavior reduces the risk of predation from visual hunters while allowing access to food. It is a strategy shaped by millions of years of evolutionary pressure, refined through consistency rather than speed. As dawn approaches, these organisms descend again, returning to deeper layers where light is scarce but safety is greater. The scale of this migration is immense. It involves trillions of individual organisms across vast areas of the ocean, forming the largest coordinated movement of life on the planet. Despite its size, it occurs without sound or disruption, guided by internal biological clocks and the slow rotation of Earth. Night also transforms the ocean acoustically. With reduced surface winds and human activity, sound travels differently across the water. Low-frequency noises, from waves, distant storms, and marine animals, can propagate over long distances. For species that rely on sound rather than sight, night does not reduce awareness. In some cases, it enhances it. Many marine mammals increase vocal activity at night. Whales and dolphins communicate, navigate, and locate prey using sound waves that move efficiently through water. These signals form an acoustic landscape that exists independently of human perception, layered and continuous. Bioluminescence becomes more visible after dark. Some plankton, jellyfish, and fish emit light through chemical reactions within their bodies. This light serves various purposes: communication, camouflage, or defense, and often appears only when the water is disturbed. Though bioluminescence can seem extraordinary, it is a practical adaptation. In a dark environment, producing light can confuse predators, attract mates, or illuminate prey. The glow is usually brief and energy efficient, reflecting the careful balance required for survival in open water. Temperature gradients also sharpen at night. As surface waters cool, thermal layers adjust slightly, influencing how nutrients and organisms distribute vertically. These changes are subtle but persistent, reinforcing the ocean's layered structure even in the absence of sunlight. For human observers, the ocean at night often feels vast and unfamiliar. Visual reference points disappear, and the horizon becomes difficult to distinguish. This sensory reduction alters perception, encouraging stillness and focus rather than exploration. From a physical perspective, however, the ocean remains active. Currents continue their slow paths, tides rise and fall, and chemical exchanges between air and water persist. Carbon dioxide, oxygen, and heat move across the surface boundary regardless of visibility. The ocean does not sleep in the human sense. Instead, it transitions into a different operational state, one governed less by light and more by internal rhythms. Biological clocks synchronize with darkness, shaping feeding, movement, and interaction across multiple species. This nightly transformation highlights an important aspect of ocean systems: continuity. Day and night are not opposites, but phases of a single process. Each prepares the conditions for the other, maintaining balance through repetition rather than interruption. For those listening, the idea of the ocean at night offers a model of calm activity. Processes continue without urgency. Movement is deliberate. Energy is conserved and directed rather than spent quickly. As darkness settles, the ocean demonstrates that reduced visibility does not mean reduced function. On the contrary, some of its most essential processes occur beyond sight, guided by cycles older than human memory. These nocturnal patterns lead naturally into broader reflections about time, continuity, and the deep stability underlying constant change. In the next chapter, we move from daily rhythms to longer scales, exploring how oceans evolve slowly while remaining fundamentally present. The oceans play a central role in shaping Earth's climate. More than any other system on the planet, they regulate temperature, distribute energy, and stabilize conditions over long periods of time. This influence is not sudden or dramatic. It unfolds slowly through physical processes that operate continuously, often unnoticed. One of the ocean's most important functions is heat storage. Water has a high heat capacity, meaning it can absorb large amounts of thermal energy without experiencing rapid temperature change. As a result, the oceans store more than 90% of the excess heat generated by solar radiation and human activity. This stored heat does not remain in one place. Ocean currents transport warmth from equatorial regions toward higher latitudes, moderating temperature differences between the tropics and the poles. Without this movement, climate extremes would be far more pronounced, and many regions would be less habitable. Surface currents are driven primarily by wind patterns and Earth's rotation. These currents form large circulating systems, known as gyres, that move water across entire ocean basins. While surface currents are relatively fast by oceanic standards, they still operate on timescales measured in months and years rather than hours or days. Beneath the surface, slower and deeper currents form what is often called the global conveyor belt, or thermohaline circulation. This system is driven by differences in water density, which depend on temperature and salinity. Cold, salty water sinks in polar regions and flows along the ocean floor, eventually rising again elsewhere. This deep circulation connects all major oceans into a single integrated system. A parcel of water may take hundreds or even thousands of years to complete a full cycle. In this sense, the ocean carries a long-term memory of past conditions, preserving traces of earlier climates within its depths. The ocean also plays a key role in regulating atmospheric gases. Through physical and biological processes, it absorbs large amounts of carbon dioxide from the air. Some of this carbon is stored temporarily in surface waters, while some is transported to deeper layers, where it can remain for centuries. Phytoplankton contributes significantly to this process. These microscopic organisms use sunlight to convert carbon dioxide into organic matter through photosynthesis. When they die or are consumed, some of that carbon sinks, becoming part of the ocean's long-term carbon storage. At the same time, the ocean releases heat and moisture back into the atmosphere. Evaporation from the sea surface supplies water vapor, fueling clouds, precipitation, and weather systems. Tropical oceans in particular influence global rainfall patterns and storm development. Despite this constant exchange, the ocean does not respond quickly to change. Its vast size and depth create inertia. When conditions shift, the response unfolds gradually, smoothing sharp fluctuations, but also delaying recovery when balance is disrupted. This slow responsiveness has both stabilizing and challenging consequences. On one hand, it buffers climate variability, preventing rapid swings. On the other, once large-scale changes take hold, they can persist for long periods. Temperature stratification within the ocean affects how heat and nutrients move vertically. Warm, less dense water tends to remain near the surface, while colder, denser water stays below. This layering influences everything from biological productivity to how effectively heat is mixed downward. In recent decades, increased surface warming has strengthened this stratification in many regions. As a result, mixing between surface and deeper layers can be reduced, altering nutrient availability and biological activity. Sea ice also plays a role in climate regulation. By reflecting sunlight back into space, ice-covered regions limit heat absorption. When ice melts, darker water is exposed, absorbing more energy and reinforcing warming trends. This feedback operates slowly but steadily. The ocean's influence on climate is not uniform. Different regions contribute in different ways. The Pacific, Atlantic, Indian, Southern, and Arctic oceans each have distinct circulation patterns, temperature structures, and roles in energy transfer. Yet despite these differences, the system remains interconnected. A change in one basin can influence conditions elsewhere through shifts in circulation, atmospheric coupling, or chemical exchange. For humans, these processes are often invisible. Climate is experienced locally, while oceanic regulation operates globally. The disconnect between perception and process can make the ocean's role seem abstract, even though it directly shapes daily conditions. Viewed calmly, the ocean offers a model of balance through accumulation rather than immediacy. It absorbs, stores, releases, and redistributes, not in response to short-term signals, but through sustained patterns. This long memory contrasts with the pace of human activity. Where societies react quickly, oceans respond slowly. Where attention shifts rapidly, ocean systems maintain continuity. Understanding this difference invites a quieter perspective. The ocean reminds us that stability is not static. It is maintained through constant movement, gradual adjustment, and deep integration across systems. As listeners settle into this idea, the ocean's role as a stabilizing presence becomes clearer, not by force, but by capacity, not by speed, but by persistence. These regulating processes lead naturally toward a broader reflection on continuity and deep time. themes that extend beyond climate into the ocean's long-term evolution. In the next chapter, we step further back, exploring how oceans change over geological timescales while remaining a constant presence on Earth. When night falls over the oceans, the surface appears calm and still. From above, the water darkens, reflecting less light, blending into the sky. Yet beneath this quiet exterior, the ocean remains active. Night does not pause marine systems. Instead, it reveals a different rhythm, slower to the human eye, but continuous and precise. Unlike land environments, the ocean experiences darkness in layers. Light fades rapidly with depth. Even during the day, sunlight penetrates only the upper portion of the water column. At night, this boundary becomes more pronounced. The surface zone loses its remaining glow, and deeper regions remain unchanged, already accustomed to near-total darkness. This transition influences temperature, movement, and biological behavior. As the surface cools after sunset, water density shifts slightly, encouraging gentle vertical mixing. These movements are subtle, but they play a role in redistributing heat and nutrients across shallow layers. For many marine organisms, night is not a time of rest, but of activity. One of the most significant nightly processes in the ocean is vertical migration. Every evening, billions of small organisms, including zooplankton, shrimp-like crustaceans, and some fish, rise from deeper waters toward the surface. This migration follows a predictable pattern. During daylight hours, these organisms remain deeper, where reduced light lowers the risk of predation. After sunset, they move upward to feed on phytoplankton and other surface resources. Before dawn, they descend again. This movement represents the largest daily migration of biomass on Earth. Although invisible from the surface, it plays a major role in energy transfer and carbon cycling. By feeding near the surface and releasing waste at depth, migrating organisms help transport organic material downward. Nighttime also alters acoustic conditions in the ocean. With reduced surface disturbance from wind and human activity, sound can travel differently. Many marine animals rely on sound for communication, navigation, and hunting. Whales, dolphins, and some fish species increase vocal activity after dark. Sound waves move efficiently through water, especially in deeper layers, where temperature and pressure create stable transmission paths. At night, the ocean's acoustic environment becomes more pronounced, shaped by biological signals rather than surface noise. Bioluminescence is another defining feature of the nocturnal ocean. Some organisms produce light through chemical reactions within their bodies. This light serves multiple purposes, attracting prey, confusing predators, or communicating with others of the same species. In calm conditions, bioluminescence can be triggered by movement. A passing fish, a breaking wave, or even drifting particles may cause brief flashes of blue-green light. Though often associated with tropical waters, bioluminescent organisms exist across many ocean regions. Importantly, bioluminescence is not constant. It appears only when conditions and stimuli align. This intermittent presence reinforces the sense that the ocean at night operates on thresholds rather than continuous display. Temperature gradients also become more defined during nighttime hours. Without direct solar input, surface waters cool slightly, reducing stratification in some regions. This cooling can encourage limited mixing, bringing nutrients closer to the surface and supporting plankton growth. In polar and high-latitude oceans, seasonal night patterns differ dramatically. Extended darkness during winter months influences feeding cycles, reproduction, and migration. Many species adjust their behavior to align with these prolonged periods of low light. Human activity does not fully disappear at night, but it changes form. Commercial shipping continues, fishing operations shift, and offshore platforms remain illuminated. Artificial light penetrates surface waters in coastal regions, altering natural cues for marine life. These light sources can disrupt migration, feeding, and reproductive behaviors. Some organisms are drawn toward light while others avoid it. Over time, this interference reshapes local ecosystems, especially in heavily trafficked areas. Despite these influences, much of the open ocean remains governed by natural cycles. Far from coastlines, darkness returns each night with consistency. There, biological and physical processes continue largely uninterrupted. The ocean's relationship with night highlights its adaptability. Systems do not depend on constant visibility or immediate response. They operate within cycles shaped by rotation, gravity, and energy exchange. From a broader perspective, nighttime reveals how little of the ocean is designed around human perception. Vision plays a limited role underwater, especially beyond shallow depths. Instead, life relies on pressure sensitivity, chemical detection, and sound. This shift away from visual dominance invites a different way of understanding environment. The ocean at night emphasizes continuity without observation, processes unfolding regardless of whether they are seen. As listeners imagine the ocean after sunset, the emphasis shifts from surface appearance to internal function. Darkness does not signal absence. It signals redistribution of movement, attention, and activity. This understanding prepares us to move beyond daily cycles and into longer spans of time. Night is one unit within a much larger sequence, connected to seasons, climate patterns, and geological change. In the next chapter, these ideas expand further, drawing attention to the ocean's long-term continuity, how it persists, transforms, and carries memory across scales far larger than a single day or night. As this journey through the oceans comes to a close, it becomes clear that what defines them most is not any single feature, depth, or region, but continuity. The ocean is not a collection of isolated systems. It is a connected whole shaped by time, movement, and balance. Across all chapters, a consistent pattern has emerged. The ocean absorbs energy, redistributes it, and releases it slowly. Heat travels through currents. Nutrients circulate between surface and depth. Life adapts to pressure, darkness, and distance. Nothing happens in isolation, and nothing happens quickly. From the surface to the deepest trenches, the ocean operates on scales far larger than human schedules. Tides rise and fall according to gravitational rhythms. Currents move across basins over years or centuries, geological processes reshape the seafloor over millions of years. These timelines coexist, layered one upon another. This layered timing creates stability. Even in regions that appear extreme, deep trenches, polar waters, or night-darkened depths, conditions remain consistent within their own context. Life persists because systems are predictable, not because they are gentle. Throughout this exploration, the ocean has revealed itself as a regulator. It moderates climate, stores heat, cycles carbon, and supports food webs that extend far beyond its boundaries. Without constant awareness, it maintains conditions that make terrestrial life possible. Importantly, the ocean does not require attention to function. Its processes continue regardless of observation. This independence from human presence reinforces an essential truth. Rest and continuity do not depend on constant engagement. Many marine systems demonstrate efficiency through stillness. Slow-moving currents, gradual sedimentation, and stable deep-water temperatures all contribute to long-term balance. Change occurs, but it is measured. Disruption is absorbed, adjusted, and redistributed. This pattern mirrors the biological rhythms observed throughout the series. Organisms adapt by conserving energy, responding selectively, and maintaining internal stability. Even in dynamic environments, efficiency favors calm over urgency. At night, when visibility decreases and sensory input narrows, the ocean does not pause. Instead, it shifts emphasis. Sound becomes more important than sight. Movement becomes more vertical than horizontal. Activity continues, but in a quieter form. These transitions are not dramatic. They are subtle and consistent, reinforcing the idea that stability arises from repetition rather than intensity. From a human perspective, the ocean invites a recalibration of scale. Daily concerns, measured in hours or days, contrast sharply with processes unfolding over centuries. This contrast does not diminish individual experience. It places it within a broader context. Understanding this context can be grounding. Recognizing that systems endure beyond immediate awareness allows the mind to release unnecessary vigilance. The ocean does not rush, yet it accomplishes vast work. Throughout the chapters, factual structures have taken precedence over metaphor. Currents follow physics, pressure follows depth, life follows adaptation. These realities, precisely because they are real, carry their own sense of quiet wonder. There is no need to embellish them. The existence of stable ecosystems at crushing depths or synchronized migrations occurring nightly across entire oceans is sufficient. As this series concludes, attention naturally turns inward. The same principles observed in the ocean apply to rest. The body regulates temperature, circulation, and respiration without conscious direction. Stability emerges from letting systems function as designed. Just as the ocean balances energy through gradual exchange, rest allows the nervous system to reset through slow, continuous processes. Nothing needs to be forced. Nothing needs to be monitored closely. The ocean teaches that awareness does not require effort. Presence does not require control. Systems thrive when allowed to operate within their own rhythms. As listening draws to a close, The imagery of vast water, layered depth, and steady movement can remain, not as stimulation, but as background continuity. Like the ocean at night, activity continues quietly, without demand. This is not an ending, but a settling. The information shared does not need to be remembered in detail. It has already served its purpose by guiding attention outward, then gently releasing it. In the same way that the ocean carries heat, nutrients, and life across distances without interruption, the mind can now drift without direction. There is nothing left to follow closely. The oceans remain, moving, circulating, and stabilizing, regardless of awareness. That persistence allows rest to feel safe, supported by systems far larger than individual thought. As this journey concludes, the invitation is simple. Allow attention to soften, as the ocean does at night. Let thoughts slow as currents do when they reach equilibrium. Nothing more is required. Good night.